Hello everyone. Welcome to my presentation. My name is Jinhua Hu from Xinjiang University. Today, I am deeply honored to present our latest work. Pure, Probabilistic Utility for Robust Evidence and Multimodal Recommendation. This is a collaborative research effort with Central South University. Modern recommender systems increasingly leverage multimodal content, such as product images and textual descriptions, to alleviate data sparsity and cold start issues inherent in traditional collaborative filtering. Recent SOTA frameworks typically employ graph neural networks to propagate collaborative signals along with item-specific visual and textual features, achieving substantial performance gains. Despite this progress, two fundamental challenges remain unsolved. First, the semantic structural gap. Standard GNNs are restricted to pairwise associations, failing to model high-order semantic relations. Meanwhile, single-view hypergraphs neglect the multi-scale nature of semantics, failing to preserve both fine-grained geometric proximity and global thematic cohesion. Second, the modality reliability gap. Existing methods follow a fuse-all paradigm, assuming all modalities are beneficial. However, raw content features are inherently noisy. As shown in the figure, indiscriminately fusing low-utility items, like case B, induces negative transfer, degrading the performance even below simple ID-based baselines. To address these challenges, we propose Pure, which shifts the paradigm from static heuristic filtering to dynamic probabilistic utility assessment. As illustrated in the figure, our architecture consists of three core components. Hybrid hypergraph construction to extract robust evidence, multi-scale hypergraph convolution with a participation-aware structural harmonization mechanism to equalize structural scales, and an evidential uncertainty learning module driven by Dirichlet distribution parameterization to regulate information injection. Let us look into the first module. To bridge the semantic structural gap, we project raw features into a unified space and construct a hybrid hypergraph reconciling two granularities. To capture micro-level geometric proximity, we construct local KNN hyperedges EKNN by linking items with their top k nearest neighbors based on cosine similarity. Complementarily, to capture macro-level thematic cohesion, we apply the Leiden community detection algorithm on a weighted KNN graph. The edge weights are computed via a Gaussian kernel as shown in equation. This explicitly clusters items with strong global semantic affinity into connected community hyperedges E. Leiden. A critical challenge here is preventing dominant structures from monopolizing information propagation. Since local KNN hyperedges outnumber global community hyperedges by orders of magnitude, a naive combination would cause micro-level structures to overwhelm macro-level patterns. Thus, we introduce a topological equalizer. We calculate the structural coverage or total participation P for each type. Then, an inverted balancing weight beta is assigned through equation to dynamically scale up the underrepresented view. This factor directly normalizes the entries of our hypergraph incidence matrix H. Grounded on the symmetrically normalized incidence matrix H, we implement multi-layer hypergraph convolution. To mitigate the notorious oversmoothing issue, we aggregate embeddings across all layers via equation to form the structure-enhanced content representation E-content. For each item I, we concatenate its raw and enhanced embeddings across all modalities into a vector Zi, and feed it into an MLP with a soft plus activation function to predict non-negative evidence values. These values represent the empirical semantic support for each modality. In the second core component, we parameterize these evidence values into a Dirichlet distribution by setting alpha as a uniform prior. Unlike standard attention, Our framework leverages subjective logic to explicitly model the total evidence strength SI and derive the epistemic uncertainty UI. After applying a nonlinear sharpening operation to the confidence score CI, we perform confidence-gated adaptive fusion. When content uncertainty is high, the gating mechanism automatically suppresses the noisy features and safely falls back to the collaborative ID embedding EID, creating a secure reliability shield. The fused item embedding is then passed into a light GCN backbone along with learnable user embeddings to propagate high-order collaborative signals on the user-item interaction graph. To optimize our model, we formulate a multitask learning objective. Specifically, we design a risk-averse BPR loss where training triplets are adaptively downweighted by their learned content uncertainty. Together with auxiliary BPR loss, hypergraph contrastive learning, and cross-modal alignment loss, the complete objective is jointly optimized. We conducted extensive experiments on 3 real-world Amazon datasets: baby, sports, and clothing. The table reports the overall performance comparison. Pure consistently and significantly outperforms all SOTA baselines across all datasets in terms of recall and NDCG metrics. The significant improvements over powerful denoising methods like Freedom and advanced hypergraph recommenders like LGMREC validate the profound synergy of our multi-scale evidence representation and evidential utility learning. To better understand our framework, we conducted ablation studies presented. In Group A, the elimination of structural components, or the harmonization factor, leads to noticeable performance drops, demonstrating the necessity of our topological equalizer. In Group B, we observe Pure's remarkable capability as a data quality diagnostician. On the noisy baby dataset, Pure effectively detects high uncertainty and relies safely on ID signals, outperforming the fixed fusion variant. On the content-rich sports dataset, it correctly amplifies beneficial semantics, matching or exceeding the content-heavy variant. To further evaluate the stability of Pure, we analyze the impact of key hyperparameters on model performance. First, we examine the structural granularity by jointly tuning the local neighbor size and global resolution parameters. For local neighbors, the performance peaks when the size is set between 5 and 10, as a larger neighborhood introduces irrelevant noise. Crucially, we observe a fascinating modality asymmetry in global community resolution. The model achieves optimal results with a coarse-grained clustering for text to capture broad thematic topics, but requires a fine-grained partitioning for images to distinguish subtle visual nuances. Furthermore, we investigate the sensitivity of the sharpening factor and various loss coefficients. The empirical results demonstrate that Pure maintains a highly stable performance across a wide range of parameter variations. This consistency validates that our multi-scale topological representation is exceptionally robust, making it highly reliable for practical deployment in diverse production environments without requiring tedious parameter searching. Moving beyond overall metrics, we conduct an in-depth analysis to verify if the learned confidence scores genuinely reflect data quality. We investigate the statistical relationship between confidence and the preference score gain over a variant where content is forcibly suppressed. As shown in the results, a clear positive correlation is observed. Items in the high confidence group yield significant positive performance gains, proving that the model actively and safely leverages their rich semantic content. Conversely, items in the low confidence group exhibit near zero gains. This demonstrates Pure's remarkable capability as a transparent data quality diagnostician. When content utility is low, our soft protection mechanism successfully suppresses the noisy features and safely falls back to collaborative identity signals, effectively preventing negative transfer. Finally, by breaking down the low confidence items, We statistically discover real-world noise types such as mismatched images and blank descriptions, validating that our unsupervised framework accurately uncovers semantic noise. In conclusion, Pure robustly advances multimodal recommendation by transforming raw features into uncertain evidence via a multiscale hypergraph and evidential gating. Thank you for watching.